Okay.
Morning. morning. You can. I prefer paper copies, and I don't mind if it's like late. But yeah, you could also turn it in on blackboard. That's fine. All right, I think we can officially start. So if you're online, say hello. I might have a few people in the chat. And so just a reminder, I think the barbecue is starting right now, but I'm going to try to end class maybe 5 minutes early so you can get out there. So it goes until 1:30, so give you guys a chance to get some food. And you probably saw them setting up right across the street, so I want to make sure you hit that up. And so other reminders, so hopefully you got an email from me over the weekend if you were not registered, but just double check that, again, you are in lab, lecture, and recitation, unless you're my one special person, but that person knows who they are. Everybody else needs to be lab, lecture, recitation. If you don't think this applies to you, come talk to me, but it probably does. So I think I'm checking my rosters, but you need all 5 of them to make that 1 credit, or 5 credits, sorry, for chemistry. It's a package for transferring. Question? Yeah, go for it. So engineering club.
Engineering club. All right, so we got some new information. I want to let you guys know that our current engineering budget for this year already is $1,200. And we are guaranteed another $2,500 if we go and do Invent Oregon, because we are the only people in the region that do Invent Oregon, so we are guaranteed 5 finalists. Another thing is you do not have, the engineering club is not, you are not required to do competitions. It is nice that if you want to participate, but we are more inclined to have it be an open hackerspace / makerspace for everyone involved. We already have 3D printers, Arduino kits, learn how to solder, or learn how to 3D print, learn how to 3D model. We have a lot of cool stuff and outreach programs we want to do in store. We are starting meetings every Friday at 1 o'clock and going until 3-ish, but you are able to come and go as you please. If you want to get in touch with me, see me after class, I will also be leaving one of our flyers with our Discord code. Thank you.
Thanks. Other announcements, don't forget about Earth Club, although I want to do outreach like Vaughn was saying, so do some hopefully collaboration, or I'll put science, whatever. We have some branding issues. Anyways, any other announcements before we get started? Housekeeping questions? Oh, so most of you found that I put our lab and homework up the front, and then you guys started making some piles, so that's excellent. And again, I'm not too strict about due dates. They're more of just write a suggestion to turn things in, and so I can grade things in a timely manner. But I do like paper copies. I'm trying to put plenty of little notations as I can, at least as I'm physically capable of doing. So sooner you turn stuff in, sooner I try to get stuff back to you. Other questions, housekeeping? All right, I think we're ready to dive in. And so this is probably a recap, but we'll start here just so we're all on the same page. And so matter can, of course, be classified to its state, so solid, liquid, gas. And we denote that in our chemical reactions. And so we'll often find, we'll write an S for solid, like let's say you're adding, iron metal, solid, plus oxygen. And then you could put a G for gas. So it gives you some sort of product. So blah, blah, blah. So that could also be a solid. And then we have, right, L for liquid. And so sometimes, right, you see water. So water could be added as a liquid phase or a gas phase. So that tells you some clue about the reaction and your setup. And then you might see this. So this will come up later in the course, but I'll bring it up. So AQ just means aqueous solution. Oops, forgot my U there. So aqueous solution. So just something dissolved in water. So mainly that's what we work with in general chemistry. And then of course OChem is just like liquid organics. And then of course we'll have the composition. And again, we're getting there. We're dancing around the subject. So this week's homework is balancing equations. A little behind in lecture, but hopefully we'll catch up. And so looking at the atomic level of what these look like. So solids, we know that matter is tightly packed, so they can't slide past, right? But they're still vibrating, so there's still molecular motion, those electrons buzzing around. And then once we add more energy, so you can add energy, and then now the particles can kind of start to slide past one another, so now they move. And of course, you've seen that with liquid, right? You can pour your liquid from one container to the next. And so usually liquid, we can say it has a fixed volume. So again, you've experienced that, so you can pour liquid, but you can't compress it, right? So you can't shove it into a smaller container. So not fixed shaped. And so solid will add, so fixed volume, fixed shape. And so then we continue, and again, we can think of water. We probably have seen water in a solid state of matter and liquid, and then of course gas as we continue to add more energy, maybe in the form of a flame from a stove or your electric heater. And so at that point, your particles get more widely spaced apart, so now they're bouncing around, moving a lot. And so what's a property of gas that we often say? What do we say gases can do? Yeah, compressible. So that's kind of the key word. So compressible. And all that means is, right, no fixed volume and no shape. And so you've probably seen that, right? You can pop a balloon and then the air goes everywhere. You can also compress it. You could compress like nitrogen all the way down to liquid nitrogen, as you can see in those like big containers. Like, you know what I'm talking about at Costco, they have those huge liquid nitrogen containers, and then you hook up your nitrogen outlet to it, fill up your tire. So gases are compressible. All right, so this is just the text that goes through it. So I'll post these notes hopefully today if we finish through chapter 2. So again, just the key points: the liquids, fixed volume, not fixed shape. We know they can flow. We can name some examples, so water, alcohol, both the type you consume and also, right, isopropanol, any sort of other alcohols. Gasoline, so that's basically octane. So octane, that's just an organic. So 1, 2, 3, 4, 5, 6, 7, 8. 8. So this is just 8 carbon chain. And so now I'm just doing shorthand. So each one of these points is a carbon and filled in with hydrogens. And so again, gaseous, we said they're moving, they're far apart, and keyword of compressible. All right, so now we have to also be able to classify matter. This starts to go into compounds. And so we have matter, and then is it one type of particle, or is it 2 types? And so, right, with this one type of particle, you're basically trying to answer, is it an element, or is it a compound? And so what's a compound? So combination of chemically bonded elements, I like that. Any other simpler definitions or like other ways to say that? So it's still true, but also so 2 or more elements, but then we still want one key phrase, or you kind of said it, it was just wordy. Yeah, so fixed defined proportions, or I like to say defined chemical formula. So some sort of, right, defined formula. And so again, y'all kind of said it, but we just want to say it right. There's a defined proportions that we know, like sodium chloride, it's always 1 sodium to 1 chlorine. H2O, so you use the term chemical bonds. So with those chemical bonds, we find, right, they always make 2 hydrogens, 1 oxygen, so that sort of thing. So defined chemical formula, so it's always the same. We can characterize it. And so good in recognizing that it's different elements. So you guys had that terminology. So we've gone over elements. So touched on those, right? Allotropes, diatomics, so don't forget those. Diatomics. So those are just the tricky elements, but again, recognizing compound is 2 or more. All right, let's do some examples. So let's start with, what are some element examples? Carbon. What's nitrogen? Uranium.
This is just anything on the periodic table, right?
Yep, so
Okay.
anything. So yeah, y'all are ahead of the game. So anything on here, we could get crazy, right, and start naming these new unknown elements that have different names depending on what periodic table you're looking at. So then what are compounds, or some examples? So water, so H2O. Salt, so which salt, what's your favorite salt?
Table salt.
Table salt, so sodium chloride. Never know, you get like potassium chloride, feeling fancy. What else? What did you say? CO2. Carbon dioxide. What else? Methane. Yeah, CH4. Any other favorite Compounds. Come on, no drugs.
Thermite.
Thermite, yeah, it's more like the reaction though, because doesn't it just produce like iron oxide? What else do we have? Any other favorites? Man, we didn't even put like caffeine. That's a mild drug. We always talk about drugs. It's either drugs or explosions in chemistry. What else?
Chemists are all drug nerds and pyromaniacs.
Yeah, that's really all chemists. All right, so had a lot of examples. And so what are some examples of mixtures? Now we have to determine, well, how do we separate mixtures? And so mixtures we'll just define as two or more substances. And again, our substances, right, is either our element or our compound. So taking our pure elements or compounds and then mixing them. And then we have these two terms, so heterogeneous or homogeneous. So heterogeneous, and they have this question, is it uniform throughout? And so I always think of food. And so with heterogeneous, right, you're going to have kind of different bites. So I always think like chocolate chip cookies or like Java chip mocha frappuccino, right? You have one big bite of a chocolate, and then by the end, it's just like some coffee. So that would be heterogeneous, and y'all can give me different examples. And then homogeneous is just uniform throughout. And so I always think, right, first bite is the same as the last bite. So Gatorade, you know, the Coca-Cola that you drink. What else? Tea is a good homogeneous one.
Would cheese be homogeneous?
Yeah, cheese for the most part should be homogeneous. Yeah.
Oh yeah, I guess it depends on the cheese.
So we'll put cheese as a homogeneous mixture, but maybe like a, you know, jalapeno cheese would be heterogeneous. All right, who wants to give me more heterogeneous examples? If you're in the chat, I am watching the chat. It can be food, it can be anything.
You know those weird fruit cakes?
Oh yeah, the Christmas fruit cakes, like the weird ones. Christmas fruit cakes. That's a good one. Boba tea. I have a boba obsession. I buy like the powders and make boba at home now. It's too expensive.
Would soil be a heterogeneous mixture?
Probably, especially, I mean, soil usually has like large chunks. And sedimentary rock, so that, it depends how homogeneous your sedimentary rock is, right? Because sometimes those can be more uniform looking, but if it has like chunks in it, so I'll put soil, right, with chunks. I'll put a sediment rock, but it's got to have like features in it, so you know, sometimes it has like a little crystal there. So it kind of depends on the rock. Yeah.
Moss agate.
So moss, agate. So now y'all are giving me rocks.
A lot of different mixtures of rocks.
Uh-oh. We spill. You need paper towels? Go along. There you go. All right. Other heterogeneous mixtures? Any other favorites we can think of? A common one, people like salad dressing is a good one. You know, it's got chunks and it's oil and water anyways. And so now let's do homogeneous mixtures. So what other homogeneous mixtures can we think of?
Somebody said soda
Oh,
earlier, I think.
soda. So vinegar, that would be a good one. Unless you're talking about like apple cider vinegar, right, where it's got the weird mother liquor floating around. So that would be heterogeneous, but yeah, just white vinegar or filtered vinegar. That's all homogeneous. Other chocolate.
Does that mean that kombucha would be a heterogeneous mixture?
Yeah,
It
as
also
long
has,
as,
like, a mother?
yeah, if the mother is still like in there, there's like particles in there, then yeah, it'd be heterogeneous. But if they filtered the kombucha and it was like totally clear, then it's homogeneous.
Okay.
Yeah, and so if like you're on an exam and you're not quite sure, right, because you kind of argue, just write in the notes what you're thinking, right? Oh, it's kombucha, it's heterogeneous though because it's got the mother liquor floating in there. So even if I'm thinking something different, right, I can see what your logic is. Yeah. Oh yeah, so whiskey, any sort of alcohol, as long as it's not like the the one with the scorpion or the worm in there. So that, so that would
$2 check.
yeah, $2 chuck. That should be homogeneous, right? I don't think it has weird particles in there. I'm not the biggest wine drinker, so.
I was joking, and there was a controversy like 6 years ago where they were finding rats
Ew,
bug particulate in that wine.
that's terrible. Oh, I see in the chat juice, so juice would be a good one. And so that, again, you could argue, right? So we could put pulpy orange juice under heterogeneous, right? But just like a regular juice or, pulp-free OJ or any other sort of juice, apple. Not sure what juice the chat likes. Yeah. Any other examples? I think we have a good list before we get too hungry. All right, so this is just the words that goes with the picture. So again, just reminding us of what the pure substance is, so elements and compounds versus our mixtures. And so of course, right, they can also vary in proportion. And so that's kind of the other key portion with the mixture, right? So there's obviously different like Coca-Cola formulations of whatever flavors they put in secret recipes, rather than, again, right, the H2O. It always is in that certain ratio, and the mixture can be changed, or now, right, they're always putting like sucralose and trying to change their mixtures. And so I think you all have a pretty good handle on the heterogeneous versus homogeneous. And so, of course, in chemistry, a lot of it is mixing stuff together and then trying to purify it. So chemistry is always like adding solvents to something, filtering, pumping it back down, adding a new solvent. It's like literally all I did in my research was pump off solvent, it felt like. And so another technique that's used, and again, we'll do this eventually in this series. I think it's second quarter. I can't remember exactly. I get all our labs mixed up. But we will distill. And so we'll do this, and of course, I don't know why the graphic has a huge safety hazard, so you would no longer distill with open flames, like this is a long gone practice. So instead you want to use a heating mantle, and so we have fancy heating mantles in our own lab that fit round bottoms, and they usually have some sort of thermocouple. And so basically, right, we have heat, we have our mixture here, and so you can either purify liquids from solids, so you could think of, right, purifying seawater, or let's say you have two liquids with a different enough boiling point, you can separate out those two liquids, at least with the simple distillation. And there's other like columns and techniques that they use to separate out closer boiling products like they do in petroleum industry. That's how they separate out all the oils. And so basically this just gets heated, and then of course it turns into a gas. Then we have water coming in that cools it down, and so then your liquid starts coming out, and then you should ideally have, pure liquid. And so, right, they do distillations for making like whiskey or any sort of alcohol as well. So I think the more times it's distilled, it's supposed to be better. But I'm not really well versed in that industry.
Why is the condenser necessary for distillation?
And it just provides a place for it to cool, right? Because once you have those heated vapors, you got to take them somewhere. So that condenser just, so notice the design. So you have your inner like jacket, right? And then the outer jacket is all water. So the water and the gases, they never touch, but it just cools it back down. And then that's what allows it to be collected as a liquid. Because, I mean, you could, in theory, right, collect it as a gas and maybe put it into a reaction directly, but that's generally not what we do synthetically, yeah.
And how are we sure that any impurities are also not going into the mixture?
So usually you don't do a simple distillation either in lab, or what I mean by this is like you wouldn't just collect one fraction. So you collect like a variety of fractions. So you are right. So like the first fraction sometimes tends to be impure, the first of coming, and then as you continue to hold it at that temperature, you just keep collecting what comes out, and then you want to verify by some technique. So usually what we do is like you take a NMR, so either a proton NMR or anything else. So personally, I used a lot of phosphorus just because I made phosphorus compounds and had to like distill them, and then you just check them, and then is it pure? And so that's where you check like your several fractions, and so you might like redistill any that have a mixture. And obviously there are other techniques. So, maybe you could take an IR as well that can tell the difference between functional groups. Later, in this course, we'll look at TLCs. So that's just a chromatography. And the basic concept, so have you ever taken like a marker and a pen and you do like that little separation? You all know what I'm talking about? Or like the inks run. So some people, yeah. But again, we'll talk about this later, but that's just another technique. So compounds, they run the same, so you can kind of verify, do I have one compound, do I have two compounds? But yeah, there's some sort of verification technique. I'll throw in there, right, mass spec. So it all depends what you're working with, what technique you're going to use. But yeah, you would check your product. And you'll kind of do this in lab, so you'll light your fractions on fire is how you'll test the purity of your fractions and see which ones light up, and those will be pure ethanol versus the ones that don't burn. Other questions? All right, so now we're going to the law of conservation of mass. And so it took a while to get here. And so, right, there's a lot of experiments going on, especially in the 1700s, of just trying to figure out what the heck is chemistry. They didn't know what air was. So, right, air and oxygen were confusing, so they didn't know air was a mixture of things. And so there was a lot of effort trying to figure out what was what. And so with combustion experiments, they sought to quantify where the heck is that matter going. Because, of course, to the early scientists, right, you burn something and it looks like it disappears. Well, where does it go? And so they eventually burned something in a container so they could actually quantify that. And so they were seeing, oh, there's some sort of gas release. Again, they didn't know it was carbon dioxide and water at the time, but just, okay, we're forming something. And so eventually, this kind of theory of the law of conservation of mass started to form. And again, it's a law, so we can prove it time and time again today. And so in our chemical reaction, matter is neither created nor destroyed, so it's just converted right from one form to the next. So it started off as some, organic compound or a packet of sugar. You burned it and made CO2 and water, right? They just went into the atmosphere, so they weren't lost, though. And so we can also quantify it. And so I don't encourage this because it can confuse people, but you can balance your reactions by mass balancing. And so we see that here. So we have 7.7 grams of sodium. And again, let's appreciate what sodium looks like. So nice shiny metal plus our chlorine gas, so 11.9 grams of gas. And so add those two masses together, and that gives you, right, the total mass of sodium chloride you expect. But we'll balance with stoichiometry, and again, we're kind of getting there slowly. And so again, this law is telling us that matter is composed of small indestructible particles. So again, a lot of effort was put in early on to kind of figure out what is oxygen, what is this thing burning, and there were, of course, a lot of things confusing about oxygen, one of those being, right, it was a diatomic, so they didn't know how it was adding. And again, appreciate, right, same number of atoms, so they're just rearranging to make our new structure here. And so there's a lot of different people involved with this discovery of oxygen in definite proportions. So let's see. So your book doesn't mention this guy, but I'll just add him in so we can, again, just appreciate how long that it took scientists to even understand oxygen. So this guy, Pelletier, started doing experiments to make tin oxide. And so he found, and again, he didn't know what he was making, but he could find that he could add what he would call 1 portion of oxygen to tin, and then he doubled that portion, and that also made a compound. So he was likely making this, but again, didn't really know it at the time. And then Proust kind of built upon his work. And so, okay, he took this tin theory and then also either confirmed that with tin, and then also, I think, did some work with iron as well. And so, again, he's saying, well, there's some sort of proportion. And so all these samples of a compound, irregardless of how they were prepared, have the same proportions. And again, at the time, they didn't know about atoms necessarily. So I think they had just discovered that it was about 78.4 parts tin versus 21.6 of oxygen. Again, they don't have an understanding of diatomics, molecular weights yet. They're just kind of figuring out masses and balances. So they're determining, right, they're always in this ratio though, or at least, or a different one. Again, depending if it's 1 or 2 equivalents. Oh, sorry. And so now let's look at kind of what kind of data they might have been looking at. So just read through this and then kind of practice your ratio. So we have 2 samples of carbon dioxide decomposed into their elements. So one sample has 25.6 grams of oxygen and 9.6 grams of carbon, and the other produces 21.6 grams of oxygen and 8.1 grams of carbon. So take a few minutes and so show, right, that those results are consistent with the law of definite proportion. And then, does anyone want to put what they did on the board? You want to go for it? Here's one marker here. Those don't function.
When you divide local compound by each other, they both equal 2.6 repeating. So that means they both follow the law of definite proportions. If I did that right. That's how I determined that.
It sounds right. I'm just plugging it in. Sorry, I'm moving slower. So yeah, that looks good. So you're verified, and so let's just go through the math. So going through them. Oops. If I could plug in the right number. So that looks good. So that was one way to do it. And so we could write that in our ratio then of oxygen to carbon. So we're finding we have, so oxygen to carbon would be 2.6 to 1. And then did anybody do it the mass percent way and figure out mass percent, or what would this be? You could also walk me through. Yeah.
Put the weight of oxygen over the total weight of oxygen plus carbon. And that gives you a percentage of oxygen.
So let's do that. Do you happen to have this number handy?
Yeah, it was 72.7%.
And was it 72.7 for both?
Yes.
So did other people do it that way? So either way, right, it showed what we wanted to show. So either that oxygen is always around 72%, or that they're in this 2.6 to 1 ratio. Oops, sorry. And let's just plug in. I'll plug in one of them just so we can see. And so, of course, right, don't forget your order of operations. I have my parentheses. And so that looks good there. So questions about that so far? So again, historically, right, they're just kind of dancing around the subject of what is oxygen, what really does it mean. So we're kind of finding things are at least in proportions, but still don't really have atoms. And so Dalton kind of formalizes a little bit further. And so again, Dalton did some more experiments. And so, of course, again, he had the issue, didn't know oxygen was diatomic, so he didn't have the correct formula. But he was, again, realizing that they could maybe go in a 1-to-1 ratio, a 1-to-2 ratio, a 1-to-3 ratio. And so also, I'll add to this, so Avogadro, so the guy who came up with the crazy number, right, 6.022 times 10 to the 23rd. So he at least started maybe realizing the possibility of diatomic, so he's the one who realized that maybe we have some diatomic elements, so that's what's going on. So all this was kind of happening around the same time, so around like the early 1800s and continuing. And so this was one of the experiments that again clued into atoms and diatomics and these different ratios. And so carbon and oxygen bothered them. And again, right, at the time, they didn't know what this was. And so later, they eventually found, so carbon monoxide is something that combines with oxygen, that you have 1 gram of carbon for 1.33 grams of oxygen. And then carbon dioxide, right, they had this different ratio of 1 gram of carbon for every 2.67 grams of oxygen.
Can you scroll back up real quick? I missed the ratios.
So this one. Yeah, so again, all we want to take away from Dalton is that it was whole numbers. And so that's something that we see, right, with our formulas that we write today. We don't have any half things. The only weird kind of half things is when you get like a water intercalated in like a crystal structure, so you might have like half an equivalent of water, but that rarely happens. So when writing our formulas, right, it's always whole numbers, since it's individual atoms, right, so discrete atoms coming together to make our molecules. And so again, all this is telling us is different ratios. So now this is hinting at where we got, right, CO versus CO2, as it's twice as much oxygen. And so that was another hint in itself. And so we won't go through all the history of this. So of course, this took some time to tease out the structure. So initially, right, they discovered the nucleus. Do you remember what famous, maybe we should talk about the history. What famous experiment led to at least the nucleus? Or, yeah, the foil experiment. So do you know what happened, roughly?
Yeah, they shot up alpha particles.
Yep.
At, they shot some alpha particles at some gold foil, and they thought it'd just go through because the positive charge, or okay, the alpha particles are negatively charged, so they'll bounce off of things that are positively charged. But they thought it wouldn't because they thought the positive charge was spread evenly among the entire atom, so the alpha particles would be strongly enough negative, or I don't actually know how that works, but they thought they would just go through. But because it's all actually centered at the nucleus, a very few of them just bounced off and hit random spots on the little detection thing they had.
Yeah, that was a great explanation. So to everybody, again, just to reiterate, so what you were saying, they expected it to pass through because they didn't know where the nucleus was. So they were at that plum pudding model. I don't know if you all talked about the plum pudding in your like history before. So yeah, they thought some might reflect a little bit, right? Some would go through, but then, like he was saying, so most of them passed through completely unhindered, and then the ones that did bounced back quite directly. And so that gave them the idea of, oh, we actually have a nucleus, but then it wasn't until later that they teased out the neutron. And so, of course, right, the neutron remained elusive since it has no charge. And so let's look at our little chart here. And of course, right, the proton and the electron, they found those. And so formally, the electron is given a negative charge. And so Millikan's oil drop experiment was famous for that. So that was pretty fascinating. So they calculated how many electrons would be on an oil drop, and they dropped it and suspended it in an electrical field. And so that gave him the charge. And he was close to the value that's accepted today, which is excellent. So that's 1.6 times 10 to the negative 19th. So that's coulombs. And let's see. And of course, right, the proton is positive. And so usually we just say, right, proton's positive 1, electron's negative 1. And then for our mass, So notice, right, again, as was verified by this gold experiment, most of the mass is in the nucleus, and we usually just round to 1 AMU, so of course, right, there's more sig figs, but we usually just say a proton's 1 AMU, same thing as a neutron, and the electron we basically say is negligible.
Is a neutron the mass of a proton plus an electron? Why is it a little bit more than a proton?
That's, yeah, I think that's, yeah, because a neutron is a proton plus an electron, because when they split, you get all the decay and stuff. But yeah, we'll talk about nuclear chemistry, I think, second quarter, if I remember. But yeah, that would account for the mass difference. But yeah, usually we just round.
Are
Oh.
those numbers something we should commit to them?
Oh, which ones? Like these ones?
The mass.
The mass of a proton. and-
You just need to know one.
Just one, okay.
Yeah, so we don't care about all the sig figs on there. We just write a proton's 1 AMU, neutron's 1 AMU. And then we'll later learn, right, you add the protons plus the neutrons, and that's the mass, but that's not the mass on there, so, but close. All right, so now this chapter is just kind of showing you different molecules. I don't quite like the order that we go in initially. That's why I always just say, hang with me, ask questions. So the beginning of chemistry is always kind of hodgepodgey, and then we'll go do like electromagnetic radiation in the next chapter anyways, which a lot of people either hate or like. So again, just kind of hang with me and ask questions. And so all this is showing is like there's different ways to show these structures. And so these are more like space-filling balls. And so notice, right, the colors. So green is generally any halogens. And so white is always hydrogen. And so notice, right, black is carbon. And so your blue tends to be nitrogen. And so again, just different structures. And eventually we'll get here so we can predict the geometry, because the geometry does dictate, of course, how it reacts, how it behaves. Is it a solid, liquid, gas? And so again, we're getting there. And so this is called more like ball and stick. So just kind of showing the bonds. But this isn't really showing like all the bonding. So this is just more like connectivity, so not focusing on like single, double, triple bonds, at least how this is drawn. And again, we'll get there. So how do we know the geometries? So all that we'll discover throughout the course.
Is there a model that does show the double, triple bonds in like physical space?
So it kind of depends. So in our molecule kits in lab, you can make double bonds on them, but it's like, what is it really showing? So like, I guess it depends like how accurate you want and like what are you really trying to see? Because like the next level would be like computational chemistry, right? And then that is actually calculating what our molecular orbitals are, and that really gives us like a deeper picture too. But it's kind of, it's a mixture of all the data, I guess is what I'm saying, right? Because it's like, what is your model really trying to show? So you could draw the picture to illustrate the double bonding, but then again, like that's also just kind of a formality because it's more about the length, right? So the length between them and then what orbitals are overlapping. So that's really what you start looking into at a fundamental level. All right, so let's go back to basics. I know, we like kind of go everywhere. So that starts to go into like MO theory, but let's go back to just kind of general, well, how do we talk about chemistry? How do we name stuff? And I know your homework is faster than the lecture right now. So just ask questions. If you need more time with the homework, that's fine. And so now let's look at how we name compounds. And we're going to start with ionic compounds, except we haven't really defined what an ionic compound is. So does anybody know what's the basic definition of ionic?
An ionic compound is when one atom loses an electron and basically gives it to another atom.
So atom, so let me rephrase that. Let's do transfer of an electron. So we have, and then what else do we want to say? And so metal plus a non-metal. So that's our other key, right? So we can identify it. So metal plus non-metal. And so let's look at the periodic table. And so remember, most of these things are metal. And so we're going to start with what I call our metal that forms kind of one type of ion. So this is our classic, right, ionic compounds and known oxidation state. And well, what does that mean? So again, it sometimes feels like we're jumping around and everywhere. But okay, let's go back to what we said. Well, we said we have a transfer of electrons. And we know, or at least we will know, so this group 1 here are alkali metals, right? They're water reactive. And why that is they have one valence electron. So I'll have NS1. So again, we're getting there. Please don't let all these things scare you, right? Again, it feels overwhelming sometimes with chemistry. But basically, all of these will give up one electron. And they will always just give it one electron. And so we'll be able to name them. These will always be 2+ oxidation state. And then we'll look at, right, our variable oxidation states. And so the periodic table I gave you is helpful, but it is not an exhaustive list. So that's why I basically labeled everything. So there are a few exceptions, like zinc is always 2+, silver is usually 1+. But other than that, right, they can take all sorts of oxidation states, even ones that are not on the periodic table, right? Like you can have nickel 1, iron 1, so those are rare, but they do occur. And so again, all this is to say these are all metals, and then anything over here is a non-metal. So they have to be opposite sides of the periodic table. And so there is some awkwardness and ambiguity over here. So usually with aluminum, and we'll talk about those as we progress. All right, so let's go back to, again, our basics here. And so we have our ionic compounds. So we said that was metal plus a non-metal. So again, the hard part is just distinguishing, is it a metal that forms only one type of ion? So again, this is usually our group 1 and 2, plus our other exceptions. So zinc, silver, and it does list aluminum, but again, I'll talk about the caveats with aluminum. Versus, is it a metal that forms another type of ion? And so again, that's all your transition metals, intertransition, and there's a few p block exceptions. So this is going to be tin and thallium, so you can have tin 2+ or 4+, thallium 1+, 4+, and lead 2+, 4+. So there are a few odd ones, but again, we'll do practice so you feel comfortable. And so notice, right, we're just focusing on simple, what they call binary compounds, so just two different elements. So once you start getting more, it depends on whether you're talking about organic compounds or what, so the naming gets more complicated. And so we see we name our metal cation and then change the ending of our anion to "-ide." And so I'll always point out like nitride. So nitride is the one that usually confuses people. So that's just right, nitrogen. And so here's a few examples. So right, potassium chloride. And so notice with all these ionic compounds, right, we don't need the prefixes because the charges dictate the formula. So potassium chloride, we can look. So our oxidation state of potassium, right, is +1. Chloride is -1. So that's how you know they're in a 1-to-1 ratio. So let's go over oxidation states at least a little bit. And so kind of jumping, but I feel like we at least need to touch on this so we can write our formulas properly. Although I think how this book teaches it, you don't need it, but. So right, this is 1+ for their oxidation state, just showing that they like to lose 1 electron. So these like to lose 2 electrons. 3+, carbon's a weird point, so right, it's 4+, 4-. And then nitrogen usually does 3-. Again, we're talking about ionic compounds. Oxygen is 2- for this group, and the halogens are -1. So if I remember correctly, your homework just has you naming the compounds, so I don't think you need the skill of going the other way, but we'll get there, which is kind of why I'm bringing it up. Yeah.
And if we forget these numbers that you just written down, where would we find these?
They should be on your periodic table, or I would write them on there.
You can see the oxidation states in the top right corner of the element. So like carbon has the +4 and the -4, but it also has a +2.
Yeah, so
I
that
don't know
would,
what that one is.
we'll get there later in this course when we do like organic oxidation states. But yeah, so they're kind of here. I think, so if you look at chlorine, I think they try to put the more common one on the bottom, although it always confuses people because 7+ is on top. But yeah, they're right on that chart, but I would write them there for your reference. So it will come up later. So again, this is kind of jumping ahead, but always feels that way with the beginning of chemistry. And so, right, we have calcium oxide. So again, we're seeing, oh, this is a metal plus a non-metal. So let's practice some. Yeah, work on those four for a little bit. And so watching the chat as well, if anyone's still there. what do we get for the first one? Somebody,
Is it lithium nitride or nitrate?
yeah, nitride. So lithium, so nitride. So again, you just change that ending to "ide." What about this next one?
Strontium chloride.
Strontium chloride. What about this one?
Aluminum chloride.
So aluminum chloride. And so I did want to bring up aluminum chloride. And actually, what's this next one?
Beryllium chloride.
So beryllium chloride. And so this is an appropriate naming, but, oh, I see it in the chat too, thank you. And so it's kind of tricky, and why I brought these two up is these are actually covalent compounds. And so yes, they are named like an ionic compound usually. That being said, you might see a bottle of aluminum chloride that says aluminum trichloride. And so how this is determined is the solid state. And so same thing for beryllium chloride. And so you have to examine the solid state structure to really tell you what's going on. So that's why I always say it's kind of tricky.
When you say solid state, you basically mean in what order the atoms are taking?
Yeah, so the solid state structure too, and this is, again, always kind of caveats with research. So to determine the solid state structure, right, you have to crystallize it out and then grow that crystal, and then they put it on an X-ray and diffract it. And so this is the solid state structure. And so you can see, right, it makes this kind of weird,
Like a chain?
yeah, so it like bonds with itself. So you can see, right, aluminum, it has 1, 2, 3, but then it's kind of sharing this other chlorine, right, with this other aluminum. So there's some sort of like sharing going on with bonding, and that does kind of make sense because we'll, again, this is kind of going ahead of the game, but aluminum trichloride, so if we just draw that, so this is what it, at least what structure we want to reflect. But again, we haven't gotten there, but we're getting there. But this violates the octet rule, so it's only has 6 electrons total, and we're going to learn, right, it's going to want 8. And so that's probably why in the solid state there's some sort of sharing. So there's what's called like 3 center 2 electron bonds, where, right, you have, of course, the bond is made here with your aluminum and chlorine. But then this aluminum is going to say, hey, I'll take some of this too, some of this action, right? And that's how you end up with that solid state structure. But that being said, right, if you were to study aluminum trichloride in the gaseous state, it could behave differently. So that's why we want to distinguish, right, this is the solid state structure. This is why we say it's covalent versus other behavior. And so same thing, we'll look at beryllium chloride. And so it's similar, right, this weird pattern. So again, it's sharing those kind of 3 center 2 electron bonds here. So that's the solid state structure. But commonly, we might just write beryllium kind of, again, oversimplified. And we might say this is a linear compound. But again, right, not reflected by the solid state. So it's all kind of, what are we trying to describe, and then what are we studying, what state. Right. Try not to confuse y'all. Oh. So now let's look at the other types of compounds where you have different oxidation states. Or do we not name those right now? I think that's what your book does.
Let's name them anyways.
Does your homework not do the multi-metal oxidation states? Probably not.
Chapter 2, I believe, has a couple of transition metals, but it doesn't really go into it that much.
All right, let's at least touch on it, and so how do we name the other ones? And so probably because we haven't taught about oxidation states, they're not really giving you an in-depth coverage, so I at least want to touch on it. Well, let's say we have iron oxide, but wait, that doesn't tell us anything. And so the problem with iron is it has multiple oxidation states, so the common ones are either 2+ or 3+. So then with that we could have different combinations. So we could make FeO or Fe2O3 as some of our combinations. And so again, why your book skips this is because we're not doing oxidation states. But what you have to do is first determine your oxidation state if it's not given to you. So again, judging from this formula, we know oxygen is -2. So that makes iron 2+, or maybe they tell it to you. But then when we name it, so now we've taken kind of an oversimplified naming, which is great for y'all. So now we can just say iron 2, where the Roman numeral is the oxidation state. And that's for your metal. So ox state of metal. And then you just name the ending normally, so iron 2 oxide. And then in this case, let's say they said, well, you have an iron and oxygen compound with iron in the 3+ state. And so now we just say iron 3 oxide. So let's just look at another one. So if we wanted to do, so manganese chloride. So what do you think the oxidation state is on manganese? Again, based off of this formula.
Where is it? I can't see it.
So you don't have to find it on the table.
I think it would.
I see some fingers. So fingers are coming up. So I see a lot of 2s. So who wants to give me an explanation? Phoenix, I saw your hand.
Because there's 2 chlorides and they each want 1 electron, so manganese would have to have 2 extra electrons in order to like share that with the chloride and then to actually bond.
Excellent. So, right, just balancing those charges. So again, if you wrote your -1 here, or learning, right, these chlorines, these halogens want an electron, and then there were 2, just like you said. So -1 times 2 is -2. So then we see, right, manganese had to give up 2. Excellent. So then we can just write that as manganese 2 chloride. And then, so this one, again, just looking at your chlorines, balancing it out. So manganese 3 chloride. Well, like I said, we'll probably revisit this later. But at least that gives you kind of a preview. And so I know your homework did cover now our binary molecular compounds. And so what are molecular compounds again? What do we say? The distinction. Bless you. What was our big key?
So metal and a non-metal?
Or that was ionic.
Oh, yeah.
So what was the other definition? So we said metal and nonmetal was ionic. So what's molecular? What do we say?
It would be,
What did you say? Nonmetal, nonmetal?
would that be like covalent bonds? It would be,
Yeah. So, right, I would just say, right, it's a nonmetal plus a nonmetal. And so I see it in the chat as well, so we could use the term covalent bonds. And I'll add to that sharing. But again, mainly looking for nonmetal plus nonmetal. So looking for things right on this side of the periodic table bonded together. And so, right, we could have silicon and chloride, so that's considered a covalent compound. So some of these on the edge. Same thing with like germanium. And these halogens, those are still covalent. So notice, right, tin goes back into the metal category. So that goes back to our multi-oxidation states. But yeah, sulfur, oxygen, nitrogen, oxygen, all these different combinations. You can have weird halogen compounds. So all those are covalent. And so now we find that these prefixes are necessary. And of course, we've learned that since, right, carbon and oxygen can combine in a bunch of ratios. Same thing with nitrogen and oxygen. So all sorts of variations. So we can't just say, right, nitrogen oxide or carbon oxide. That doesn't tell us anything. And so the prefixes we want to use for both atoms in our covalent compound. So you don't need to use mono if it's the first element. So we don't usually say, right, monocarbon, monooxide. We just say carbon monoxide. But then we want to use all our prefixes for our second element. Should probably just name all of these for formality's sake, if I can move them. One more time. All right, take a minute to name them, and then we'll go over them really quick. All right, are we ready? And y'all can just shout them out. Let me just-
carbon monoxide.
Carbon monoxide.
Carbon dioxide.
Oh, I can't write too. Carbon dioxide. I know I have terrible handwriting. Trying to make it better. Next one.
Nitrogen monoxide.
So nitrogen monoxide. And that was a question in the chat, and yes, we have to do that mono for all the second elements. So what's the next one?
Dinitrogen monoxide.
Dinitrogen monoxide. Next one?
Nitrogen dioxide.
Nitrogen dioxide. And our last one here,
Dinitrogen trioxide.
dinitrogen trioxide. Wow, I can't spell, apparently. So those covalent compounds, they should feel relatively simple to name. Are there questions on these? And so, right, I'm not a speller. You can kind of tell that. And so this usually doesn't come up since I give a lot of paper assignments, but it will come up on like the reading questions. So if you like misspell something and you get it wrong, just let me know and I'll fix it, because I'm pretty bad at putting the right vowel in there. So, you know, I'm totally lenient on spelling. So same thing on your exam. All right, just at least make sure I can decipher what you mean.
So if molecular compounds are this, if molecular compounds use covalent bonds, does that mean that binary compounds use ionic bonds?
Well, the binary, like the metal ones, because they call these binaries as well. So yeah, binary ionic compounds are metal plus non-metal.
Gotcha. Okay.
And so now this is going through how to figure out our formula mass or molecular mass. And so this is also like abbreviated a million ways. So you can sometimes see like AW for atomic weight, and it all means the same thing. Formula weight, molecular weight. And so we're either talking about the individual mass, so if we're in AMU, and so let's just go through this water example. And so this is just adding up, so we can look at the periodic table, and again, you might have some rounding discrepancies if this comes up on, again, most likely the reading questions where you have issues, but just let me know. So it's all just rounding. And so we just take, right, our masses from the periodic table, and then you add them up. And so notice, right, they rounded more, so you could, again, have different answers. I'm not too picky on this, how you want to round. But basically, so you add them up, and this either gives us the weight, or at least the average weight of one atom, if again we're in AMU, or we say, right, 1 mole has a weight in grams. So let's practice a few masses. So let's do the weight of this compound, and let's look up another one. So work on those two.
done the calculation, the units for that would be grams per mole, right?
Yeah. Unless you wanted to put in AMU, so. Yeah, as long as you're comfortable going back and forth and recognizing. We'll give people another minute or so. I still see pencils and calculators going. So let's at least start with our silicon tetrachloride here. So I'll at least name this one. So what do we get for that one?
169.90 grams per mole.
Is that what other people got? Just thumbs up, roughly. Excellent. And of course, right, you might have different endings here just depending on how you round it or where you pulled your numbers from. And then what about this one?
I got 194.194.
194.194. That sounds pretty good. Is that what other people got? Just some thumbs up. See some nods. Again, might have some rounding discrepancies. Yeah.
I got it correct for the second one, but not the first one. How did you calculate the first one?
So let's see. So silicon, did you plug in? And so double check that you don't have a calculator error. So plus, so chlorine 35.453 times 4. Is it a calculator or this punch?
I have tens that times 3 and
Yeah. So always, right, show your work. So on your exam, right, at least lay out properly what you should punch in and everything. So there's usually some sort of calculator error that happens with students, but as long as it's all laid out, I can at least give you most of the credit. Other questions? Yeah.
If we do something like this in the homework, would you want us to use the masses on the periodic table you gave us? Not like the periodic table
Oh,
that has, like,
I'm not that picky where you,
Oh,
yeah, pick the numbers from. Again, the only place where that becomes an issue is maybe the reading questions, but then you just shoot me an email and, I can double check that. All right, I think we have some time to at least start chapter 3 before I let you sneak out of here. So now chapter 3 starts going into our chemical changes. And so what is a chemical change? So again, we just alter the composition by rearranging our atoms. So like we've been emphasizing, we're not poofing anything magically. It's just rearranging our atoms, right? And we're not talking about nuclear reactions right now. Yes, we will touch on that later in the course. And obviously, right, those change identities, but that's kind of a special category. So we're just focusing on chemical changes where we're, again, just rearranging our atoms. And so if we zoom in, so I'm sure everyone has seen some rust forming somewhere. And we start off with our nice iron atoms. And then, of course, oxygen is hanging around in the atmosphere. And so eventually that rearranges and changes structure to make that rust, which of course starts to break off and makes it more fragile. So of course changing, right, its structural integrity. And this process can also be accelerated by water and salt. So we don't have this on the West Coast. I noticed, right, we salt our roads with like rocks. But in the East Coast, I don't know if they still use a lot of salt out there. But they always say, right, don't buy a car from the East Coast. Well, that's because they use salt on the road. So that means the undercarriage of the cars tend to rust out. Or that's why they say, like, go wash your car in the winter in the East. So all that is from our rust. And so we get our new compound. And so this is, again, our multi-oxidation state. So notice iron. So that's our transition metal. But they told us here, right, it's an iron 3 oxide. So telling us this iron is in the 3+ oxidation state. So that's one of the more common oxidation states of iron. And so this is something super important. So you would do this probably every day of your life, multiple times a day. If you are a practicing chemist or if you do research, right, you're always writing out what your equation is, even if it's, right, sodium plus chlorine gives you sodium chloride, or whatever your advanced, right, molecule is plus whatever you're trying to study. So you always want to write out, what am I doing? That's very basic. And so again, they're involving a rearrangement. So we want to be able to write out our reactants and our products. And so there's a lot packed into this statement. So it's giving us, right, quantities, the chemical identity, and their physical state. So we get the quantities from our ratios. And so your homework goes over balancing. But notice, right, we want to write the same amount of atoms on the left side as the right side. And so we have 1 carbon on our left, and we can do some accounting. 1 carbon on our right-hand side. And then they've gone ahead and balanced it, it looks like, with our 2 coefficients here. And so we'll learn, right, that's how we balance equations, by determining the ratios that we add our reagents. And so going through, so I have 4 hydrogens. And so that's why they have a 2 here. So we have 2 hydrogens and H2O. This 2 gets distributed. And so now 2 equivalents of O2. And so again, this is important when you write your chemical equations. Don't forget your diatomics. So you don't want to have 4O, right? That's not proper. It looks like 40 anyways. So we don't want to write that. So write our diatomics. So that's 4 oxygens. And so now we have 2, and then distribute the 2. So 4 oxygens. Yeah.
How do they figure out the oxygen wants to pair up with nitrogen and the H2O? Like, how do they figure out that the reactant's going to turn into this switching product?
So this is done right over characterization. So you would have to somehow determine this, and it's also like figuring out, well, what else could it be making? So part of that is just like learning how things react. And so now we know, because, right, we've been doing these sort of combustion reactions, and so now we can define it, right? So we can say, well, this is a type of reaction called a combustion reaction. And again, we'll get there, but we know the products of a combustion, or how a combustion works. It's some organic, right? So carbon, hydrogen, oxygen. In this case, right, no oxygen, but that's fine. It could be 0. Plus some equivalents of oxygen, and so you would have to determine that by balancing. But it always gives you CO2 and water for any combustion. And so we'll learn this again as we go through, like recognizing types of reactions. And so this is, again, a common type, but at some point, right, somebody has quantified that and measured the gas in some way. And again, it's depending on what technique they use, NMR, mass, this would come up good on an IR, but it's all just whatever technique they were using. And of course, now we just keep verifying it. Does that answer the question?
Kind of, yeah. Would there be a way to mathematically know what it would be, given a reactant? Like you could put in a different reactant, know what product would come out?
I guess it would depend on like the mass. So maybe you're talking about like figuring out by mass. So that's something that you could do. But yeah, you have to quantify it. So if you quantify it and then you know law of conservation of mass, that could be another way to help you determine. Because again, there's only so many permutations from this. And so like we saw, there's a lot of information packed in there. So we have the states, so gas, 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 liquid. And so like we saw earlier, again, we can use those abbreviations. And this helps the practicing chemists know, like, what am I going to do? Like, how am I going to plan to react them together? And of course, there is also, with a published paper, there's usually some sort of prep that goes along with it. This is also useful, and that prep will also tell you how you actually add them. And so like we're seeing, we get the relative number of reactants and products. So again, we use our big coefficient then to write those ratios. And so we can either, depending what information we have, we can use our weights, we can use stoichiometry to figure out how much product we will make. And so quantities in chemical reactions, so again, the amount of every substance used and made is related to all the other amounts. So again, we have the law of conservation of mass and balancing equations by balancing atoms. And so stoichiometry is just what this whole thing is called, is figuring out like how much stuff do I need to weigh out and how much stuff do I expect. And so again, if you're a practicing chemist, you're doing this all day, every day, basically. And so this is just emphasizing our atoms, so we can count them, we can look at them individually, and we can see how they arrange. So kind of going back to your question, how do we know what the heck we're making? Well, we kind of start to see these patterns and bonds that tend to form, and then we can predict. All right, so see if you can balance this equation.
Is that, oh, never mind.
Yeah, it's like cobalt oxide plus carbon gives you cobalt plus CO2. Does anyone want to throw it on the board for us? Let's see. Let's go bonds. Let's switch off our victims. And so something to look at is you might want to see, well, who should I start with? And right, you have carbon by itself, cobalt by itself, but oxygen is always paired, so you could try to balance the oxygens first. And this is a game of kind of guess and check. Let's see what we get. Let's try a 2. And then a 3, so just balancing our oxygens first.
So my method was, we have 3 oxygens over here, no matter what. We have 2 oxygens over here, no matter what. 6 is your LCD, and then now you have 3 carbons and 4 cobalts.
That looks good. Did everybody get this? Any questions or anything? And so, of course, right, if you looked at the homework, I'm sure they get harder and trickier. But just, right, keep guessing, keep checking, and kind of play with it. And so how do chemicals react? And so this is pretty cool. So Mendeleev started arranging the elements kind of in our periodic table. And so you'll actually play with this in lab of kind of going through the thought process, the patterns that they saw. And so again, they're trying to figure out how to arrange them. So they were going by increasing mass, but you'll see in lab kind of the issues with that. But then also looking for those properties that recur. So going back to our alkali metals, so recognizing, well, lithium is really water reactive, so is sodium, so is potassium. And so why is that? Arranging them that way. Oops. And so Mendeleev will also learn in lab that he predicted elements that weren't isolated yet. So in this case, he predicted gallium. So didn't know what it was, but just figured it should go under silicon. So if you look, so silicon, and so gallium was over there. And also germanium, so that is under silicon. So again, predicting those existence. And so again, he tried to arrange them in increasing mass, but now we've kind of refined that to be atomic number. And so why do we use the atomic number? Does anyone know what that corresponds to?
Because the number of protons doesn't change between isotopes of the same element?
Yes, so it's defined by the protons, and I like what you said, right? Each proton, so that's consistent with the isotope. And so we'll just say, right, number of protons defines the element. That's another way to say that. And so later we'll touch on isotopes, what exactly those are. But yes, the atomic number is better, more reliable, and defines the element. And so our rows are referred to as periods. And so again, as we kind of march through the course, we'll learn that this corresponds with our kind of major energy levels to some extent. And so essentially, right, as you go down the rows, you keep adding more and more onion shells of your basic atomic structure. And then the columns are just called groups or families. And of course, they're called families since they have similar properties and similar reactivities. And so, right, he just recognized the pattern, but he doesn't really explain why the pattern occurs. And that's what we're going to be diving into as we kind of dance around it and delve into it is, right, these valence electrons, all these oxidation states. So all these kind of terms that we're throwing out there, we're really going to keep diving into how we predict reactivity and all those properties. And so we can look at our periodic table. So there's often different ways to group it. And so these are considered kind of main group elements, or though usually when people say main group, they care about these ones in particular, kind of main group research. And then, of course, we have our transition metals, and then our intertransition metals, but these are also just called lanthanides, actinides. And again, different level of detail. So this one breaks it up into alkaline metals or alkaline earth, transition metals, and then you kind of have your basic metals, metalloids, right? These are kind of your awkward ones on our periodic table, and nonmetals. And then again, lanthanides, actinides. And so now we'll look at kind of their charges again and their properties. And so again, most of these elements are metal. And so looking at our alkali metals, we just have one more electron than the previous noble gas. And I usually say, this is again NS1. So they all have one valence electron. And so that's where we like to say, well, they tend to lose that one electron, especially making ionic compounds, and that's where we get this 1+ charge or 1+ oxidation state. And so moving over to the alkaline earth, so these tend to be a little less reactive now than our alkali metals, so usually they're reactive with acids. And so of course as we move over, so now they have one more electron in their valence shell, so sometimes NS2 is our abbreviation. And so that's where that 2 comes from, so they do have 2 electrons to lose, so then they make cations with a 2+ charge. So again, write those oxidation states, 1+, 2+, you haven't. All right, so now we start looking at our electron configuration, but I will probably stop here. All right, so let's stop here. So we'll pick up on Thursday with going back through electron configuration and starting to, again, try to make more sense of all these charges and oxidation states. So ask questions, of course. And so don't forget the barbecue. I'll hang on stream in case there are any questions. And then otherwise, I'll see everyone in lab.
returned the popcorn letter earlier?
Oh, no, it's due like this week.
Okay,
I think so.
it is done, and there's like a pile there.
Oh,
So
yeah.
can I just like?
Yeah, you can either join the pile, or if you're not ready to turn it in, you can just give it to me another day.
Do you want me to bring you food?
No,
I thought it was through the night already.
Yeah. Do you clean up everything?
Yeah.
Sorry, I was trying not to kill you guys with paper towels, but trying to help. All right, I'm gonna stop this stream.